See, wait. See, how will you get ABC? You have an AND gate, you connect ABC, right? Then how will you get A, B bar, C, D? You have an AND gate, you connect A, B bar, C, D. Ah, you have EF bar, you connect E, F bar, correct? Then you have AD, hmm, AD, and then you will take these things, right? Hmm. Okay. Uh, this is connected to an OR gate. Okay, now to get this B bar, you should have actually connected a NOT gate and given B here, right? But they're saying ignore that part. They're saying this B bar is already available with you. B bar is already here with you. Okay. How many input ports are there here? This has three input ports. This has four. This has two. This has two. How much is that? 11. And here you have 4. 11 plus 4. You have to consider B bar is directly given to you. Suppose this was not the case, then for B bar you would have to use one NOT gate, right? From B to B bar. And then from F to F bar, one more NOT gate would have been there. So there are two more input ports here. One input port with both the NOT gates. Then that answer would have been 17. Since they have told you that the complemented form of the input is already given, then you don't need to do NOT gate to have a NOT gate. That's why the answer is 15. It's not confusing. Hmm. B bar is not an inverter. B bar is not an inverter. B is an input. B bar will also be the output of that inverter, but it's still a variable. B bar is not a circuit. Inverter is a circuit. This NOT gate is a circuit that has an input and output. When you write B bar, if you want to get B bar from B, then you use a NOT gate. But B bar itself is not a NOT gate. Okay, that's how it is. Okay. So it is actually 15. 15 is correct. Does anybody else have a doubt in that question? Somebody who wants to challenge the answer. Or if you are not convinced, you can raise the question in the uh, discussion group also. Okay. You have all watched the lectures, right? This is just some points I wrote down. When you're, if you want to go through this live session again, then you can see a few points that I've written down. I'll just scroll through these things and you guys tell me if you have any doubts in this. Lecture 16, do you have any doubts? They've explained about XOR function and XNOR function. XOR is an odd function. That means if there are odd number of inputs that are high, it will give you a high output. And XNOR is an even function. That is, if there are even number of ones in the input, then you get a 1 as the output. So you can use XOR to get even parity, and to check that even parity, you can use XOR again. Similarly, odd parity for XNOR. In lecture 17, they explain the CMOS inverter circuit, how you get a inverter using CMOS technology, using a PMOS and NMOS transistors. They You were taught about pull-up networks, pull-down networks, uh, making a NAND with CMOS, NOR with CMOS, and a slightly more complicated situation. Then you were taught about matching the logic levels. So the output high and the input high should uh, be within certain parameters to get a good circuit. Then timing diagrams. You learnt about static hazards and dynamic hazards, which are caused by gate delays. In lecture 19, okay, for the people who joined now, if you have any doubts in the lectures, you can ask. I'm just going through some points I wrote down from each lecture. Lecture 19, you are taught a method to eliminate static hazards when it's a two-level circuit, and you add redundant groups in the K-map. Lecture 20, you are taught a few arithmetic circuits: adder, half adder, full adder, ripple carry adder, subtractor, and then finally it ended with the carry look ahead adder, just so that you can save time on the propagation delays by already calculate the carries earlier using the simple OR gates and AND gate. Okay. Any doubts in the lecture or previous week assignment questions? Noise margin. I actually didn't explain much. I just scrolled through the points that I had written. And if someone has a doubt, you can ask when we get there. Okay. Logic level matching. Hmm. See, suppose you have an inverter, like I have shown here. You have two inverters and you have connected one after the other. Then a VOH is kind of a threshold for the output level. Okay. When the output of the inverter is above VOH, you consider it as a logic 1. So when your computer or whatever circuit it is, when you feed the output voltage to that circuit, as long as it is above VOH, we consider it as a logic high for the output. Same way VOL, if the output is below VOL, we consider it as logic 0. Now you could have set this level, set both the levels equal to the middle of the max voltage and the minimum voltage. So if this was 5 volts and this was 0 volts, this is 1 and this is logic 0, right? But when you get the output from a circuit which it could be any real number, it might not be at 0 and 5 volts exactly, right? So suppose you get some voltage here, so suppose your inverter gives you a 4 volts, then what are you supposed to consider this voltage as? Would you consider it logic high since it is closer to 5 volts? Would you consider it logic low anyway? Okay, so first you might think that you will have a voltage here, middle point, and it's at 2.5 volts. Then if it's somewhere here, if you get 2.6 volts, then it will be high, right? If you choose your threshold here. But the problem is in these circuits there might be noise. And if the noise uh, is subtracted, that is, if you get destructive noise, then your output voltage might actually go below. So you might get 2.4 volts when you're actually supposed to get 2.6 volts. Now what will happen? Yeah, just a zero point 0.2 volt difference here caused your output to be completely different, right? Instead of 1, you got a 0 in terms of logic levels. So we want to avoid this situation. We don't want such small noise to interfere with the working. So what we do is, instead of getting one single threshold level, we set two threshold levels. One is for the high voltage VOH, one is for the low voltage VOL. And we say that if it's above VOH, we'll take it as logic 1. And if it's below VOL, we'll take it as logic 0. And if it's in between, we say that there's some problem with the circuit and we won't consider it as a proper output. We won't deal with outputs that are in this section. Okay. Uh, you did you at least understand this definition? Ah, and the thing is, this threshold that we are setting, it's different for the input and the output. So if you have an inverter, for the output voltage, you'll have different threshold values. See, it's closer to your max voltage. It's closer to your source voltage, and this is closer to your ground. The distance is small. And for input, we consider different thresholds. That is, when you are giving the input, as long as you give something that is here, it will be considered as high by the inverter. Okay, but suppose you gave this voltage level, that same voltage came out of the output of this inverter, then you would say, okay, this is not something that we need to consider. So you can't really decide if it's high or low, right? So there are different threshold values for the same inverter for the output and input. So when you consider two of them like this in a cascade, then there is some difference here, right? So why is this difference useful? Suppose due to some noise, the actual voltage that you got, instead of being at 5 volts, or instead of being somewhere here, drop to this level. Okay, now according to the output, it's not really a high signal, right? But actually you did get a high signal. You were wanted to send a high signal. So when you look at the same voltage from the perspective of the input of the second inverter, for that inverter it looks like a high signal, right? So you got what you wanted, but there was a lot of noise that was added to your output. So you get kind of leeway where even if this amount of voltage, whatever the difference VOH minus VIH, if this amount of noise is added to your output, then the next circuit or the next inverter will still take it as output high. so there won't be any errors. That's the concept of noise margin. So how much noise can you allow? What margin of noise can you allow in the output of one circuit such that the following circuit will still consider the uh, input to be the same as the output that you actually wanted to send. And this is how I understand noise margin. The definition that you gave, I don't know. It might be correct, but is there any problem, Animesh? Okay, I'll explain. See, it doesn't need to be two inverters. Suppose you have some gate here, okay, and you have some other gate here. Well, to define noise margin, we use the same gate. Okay, let's assume they are both NOT gates only. This is a NOT gate. This is a NOT gate, or it could be AND gate and AND gate, whatever it is. So you understood why the two separate thresholds are used for output and for high value and low value. This threshold exists both for the output and the input. So if you consider only one circuit, one NOT gate like this, okay, and usually it will be connected to some 5 volt and ground. You saw that CMOS circuit, right? CMOS NOT gate was somewhere. Where did it go? Something like this. Here, this VDD, this will be plus 5 or plus 12, depending on what uh, transistor you're using. You'll have different values, and here at the bottom, it is connected to ground. So, uh, for this inverter, let's say VOH is 4 volts. Okay, this is 5 volts. This is for output. This is for input. Let's say for the output, as long as the output is over 4 volts, you say that it is a 1, a logic 1. Okay, and as long as it is less than 1 volt, you say it is a logic 0. Fine. Suppose you connect it to some circuit, you get some input here, and then your output, it turns out to be 4.2 volts. Then, as far as this inverter is concerned, what is the logic value of the output? 1. So this inverter wants to tell the future circuit, whatever it is, the succeeding circuit, that it is giving out a logic 1, right? And this circuit should understand that this 4.2 volts actually means a logic 1, right? And suppose this output is actually 0.8 volts. Then since 0.8 volts will come somewhere here below 1 volt, then this inverter is actually trying to send out a logic 0. And the circuits after that, whatever circuit is there, that should also understand this 0.8 volts as a logic 0 only. That should have to interpret it the same way. Suppose here, uh, that is with respect to the output. Next, for input also, we have threshold values. This is VOH, is VOL. What threshold values you have? Let's say this is at 3 volts. Okay, that means if you give an output, an input to the inverter above 3 volts, then the inverter will think, okay, I've got a logic 1. Okay, this is the threshold for the input, VI high, for the high level. This is VIL. Let's say this is 2 volts. VIL is 2 volts means that if an input less than 2 volts is given to this inverter, then it will interpret that as a logic 0. So if you get 1.8 volts, it's less than 2 volts. So this inverter will think, okay, I got a 0. So this output stage and input stage have different threshold values. Did you understand till this part? Okay. So what is one advantage of having these different values of threshold for input and output? Uh, let's say you have a cascade of these circuits. Okay. And some input is given to this inverter. It interprets this input as 0. Let's say the input here is logic 0, some voltage that is logic 0. So it should be less than 2 volts. Let's say somebody gave 1.5 volts here. So this inverter is supposed to produce a logic high at the output. At the output, what would be considered logic high? Something above 4 volts, right? Animesh is. Did you understand? See, let's uh, let's say this is some circuit that you don't know. It's some black box. It gives some output. Let's say it will give a voltage of 1.5 volts here. That will be carried by this wire, and if there is no resistance, then the voltage will be the same throughout the entire length of the wire, right? So this will also be at 1.5 volts, the input to this. So this 1.5 volts, is it a low or a high? How do you decide? No, you don't. Why is it low, Venkata? Why is it low? How do you know it is low? In I have given my threshold levels, right? See, that is wrong. You're looking at the output. Why? This thing is for the output, right? These threshold values are for the input. Ah, So that's what I am telling. This input and output have different threshold values. What is considered low for input might not be low for the output. What is considered low for the I've already given, right? For input 2 volts and 3 volts. Yeah. For output it's 4 volt and 1 volt. Now see, you get 1.5 volts. This inverter will look at this 1.5 volts and check with the input threshold, input low threshold. So 1.5 volts is less than 2 volts, which is the V input low. If it's less than V input low, it decides, okay, this is logic 0. Okay. Once this inverter decides it's logic 0, it says, okay, since I got a 0 as my input, I have to send out a logic 1 as my output. Right? It's an inverter. So if it sends out a logic 1 as the output, if the output must be logic 1, what is the acceptable voltage value that it can send out? No, now it is the output, right? Ah, yeah, it should lie between 4 to 5 volts. Ah, first look at only the first inverter. Think about what the first inverter will do and think. See what the first inverter does. It sees 1.5 volts. Then it will see VIL and VIH. What is VIH? 3 volts. What is VIL? 2 volts. This 1.5 volts is less than VIL. That is less than 2 volts. So it will say I got an input of logic 0. Since I got an input of logic 0, I have to send out an output that is logic 1. And for an output, you consider 4 to 5 volts as logic 1. Right? I have given a definition here from 5 to, yeah. So as long as it sends something between 4 to 5 volts, this first inverter is happy. It doesn't care anymore. Let's say it tried to send out 4.5 volts. Uh, if it sent out, if there is no problem, it sent out 4.5 volts. From first inverter's perspective, it sent out a logic 1. It doesn't care what second inverter does. Now the second inverter, at its input, it will see 4.5 volts. And what will it think? Yeah, why does it think that? Yeah. So 4.5 is above 3 volts, right? That's why it will think it is a logic 1. And since it's a logic 1, it has to send out a logic 0. It will send out something between 0 to 2 volts. Let's say it sent out 1 volt. Both inverters happy now. Okay. Suppose there was no difference between the input and output thresholds. Yeah. So for input, this is VOH. No. Uh, wait. For output, this VOH, VOL. This is at 1 volt. This is 0. And the same thing holds for input. Okay. Consider this case. Okay. Now, let's say again somebody sent this 1.5 volts. Since it's 1.5, this okay. Wait, not one. Let's not say 1.5. Let's say somebody sent zero point 0.5 volts. The input this inverter sees zero point 0.5 volts. This zero point 0.5 volts is below this 1 volt. Since VIL VOL both are equal, I have set them as equal. So it will check if it's below VIL. VIL is 1 volt, so it's logic 0. It has to send out logic 1. Now, logic 1 for the output is between 4 and 5 volts. So it has to send something between 4 and 5 volts as the output. Let's say it wanted to send out 4.2 volts. Okay. Somebody did some mischief. They introduced some noise here, and this actually reduced to 3.8 volts instead of 4.2. Okay. We don't know why that's happened. Something went wrong with the circuit. Now you have a 3.8 volts at the second inverter's input. Now what happens? This VIL is same as VOL and VIH is same as VOH. VIH. So this 3.8 volts, is it high or low for the second inverter? Yeah, it is undefined because it's not between 4 and 5 volts. So this circuit, it says, okay, you are giving me undefined input. I won't care. I'll give whatever output I want. It might even fluctuate that output. We don't know what will happen. It might even give you something. It might give you 5 volts itself. It doesn't care. It says you are giving some bogus input to me. But you are supposed to get a logic 0, right? 0 becomes 1, and this 1 should become 0. So you are supposed to get logic 0, but you actually got 5 volts, which is logic high. So this is a problem, right? This would mean that there's not much tolerance to noise here. So that's why, suppose, like the previous case, this output and input thresholds were different. And the input high threshold was actually at a lower voltage, and the input low threshold was actually at a higher voltage. Now what will happen? You gave zero point 0.5 to the input. It considered it as logic 0 and it wanted to send logic high. It tried to send out 4.2 volts, but it actually sent 3.8 volts. Now, this 3.8 volts, what will the second inverter think about it if these were the thresholds? Yeah, because it is above 3 volts. So, it will see, okay, I got a logic 1, I have to send out a logic 0, and it will send out something zero point 0.5 volts or something, whatever it is. So, even though there was some error here, even though the output actually went below the specified threshold that I had given, I said 4 volts for the output is high and below that it's undefined. But the second inverter still understood that as a high voltage, right? That's the noise margin. How much below the threshold can the output high voltage go, such that for the next inverter it is still considered an output high? That is 4 volts minus 3 volts. If you go below even 3 volts, instead of 3.8, if you got 2.5, then again there would be a problem. This would say that the input is undefined. So you can go up to 3 volts. Did you understand now? Okay. Hmm. Okay. Does anyone else have a doubt in the lecture topics? Okay. Ah. Ah. Yeah. Yes. See, when you connect in this circuit, uh, where was it circuit? This is the actual circuit, right? In practice, this will how this circuit inverter circuit will be. Okay, that is a NAND gate. Where is the inverter? This is the inverter. So this is at 5 volts, and when you give a 5 volts, you say this switch is closed and this switch is open. It's like this. So this whatever 5 volts is here will come here or something like that, right? Wait, uh, it is the opposite way. So if you give 5 volts here, this will be open and this will be closed. So you're supposed to get 0 here since the ground is at 0 volts. But the problem is these circuits, they are not that good. It doesn't behave like an exact switch. This thing might actually be at point 0.5 volts. This thing might be leaking some current here. This PMOS transistor, and this thing might not be able to drain all the current here. It might not be able to get pull down this output to 0 volts exactly. So no matter what you do, this level will be below 5 volts. Then what will you do? You have to have some kind of interpretation, right, of what you will consider. Yeah, the inverter doesn't really care. But to tell somebody that your inverter is actually working properly, then you should be able to, at least with some certainty, say whether your output is at high or low. Yeah, depending on how the transistor characteristics are, you might get different things here. And like you said, from a design perspective, the follow-up circuits, whatever are there, should also be able to interpret it correctly. They should also be able to work properly. And yeah, this thing, I think if you take a course on VLSI design, these concepts will be taught in more detail. This design, how it happens, and what threshold values you will get. They will actually draw the characteristics of PMOS and NMOS, and then they'll tell you when you can join them what will be the characteristics and which region you can take reliably as high and reliably as low. So all those things, if you study a VLSI design in a VLSI design course, you can understand better. Okay. Anyone else? Uh, which type of circuit? Is that what you're asking? Uh, hmm. No, that was one example was given in the lecture, right? One example was given for static one hazard. I think they gave an example circuit. No, see, static hazard and dynamic hazard, these things, they are there for you to understand. It doesn't mean that one type of circuit will only produce this or one type of circuit won't produce that. Uh, if the hazard is occurring in some circuit and it occurs in the way you define, that means static hazard is occurring. So, where is it given that only dynamic hazards occur in combinational circuits? But that doesn't say static hazards don't occur, right? It says dynamic hazards will occur in these situations, but doesn't say static hazards cannot occur. Okay, it may occur, but they may have that circuit might be special. It might have been designed in such a way that no hazards occur. Or if it's a very simple circuit, then there some method was taught in the lecture, right? Adding redundant terms in the expression can eliminate static hazards. In lecture 19, one example is given. Yeah, so let's say you have some circuit that's like this. A bar. Then see initially, let's say for a long time A was at 0. Wait a minute. What did I even write? A, A bar. So let's say A was. Let me write it in a new page. So let's say for up to time t0, your A was low. It is at this value. Okay. Then your A bar for that time it will be at high, right? That's correct, right? In steady state. Okay. Now let's say your A changes to high. Okay. Now your A bar was supposed to go low like this. Like this. It was supposed to go low and continue. But what happened is this NOT gate. This NOT gate has some delay. Let's say it's 10 nanoseconds or something. Then instead of suddenly going low like this, it will go low after 10 nanoseconds, right? Oh, okay. And let's say this was an AND gate. This is your output. Oh, what will be the output? You are doing y is equal to a bar, right? It should always be 0. So initially, up to time t, A bar is 1, A is 0, so you will get 0. But observe from T0 to T0 plus 10 nanoseconds. Here A bar is also 1, right? A is also 1. So you will actually get 1. And then from here onwards, let's say it's time T1, this is low and this is high. So you will get a 0. So for some amount of time, this output that was supposed to stay at low at all times actually went to a high voltage. That's a static 1 hazard. Or is it a static 0 hazard, I think. Yeah, static 0. So it was supposed to say static at value 0, but it actually went to high in between. Did you understand? Okay. Does anyone else have a question? No questions. I'll move on to problems then. Ah, I didn't understand your question, Animesh. W- Have they given you the input values? Have they given you any delay? If they simply ask you to write a timing diagram for the expression a plus bc, I am not sure what to write. You should raise that question with the TS. But usually they'll give you the inputs. They'll give you how the inputs are changing, or they'll give you what is the delay in the gate, or from which state to which state the inputs are going. Something like that will be given. Yeah, they'll give you say a plus bc was bc bar or something was there. They'll say okay, what will happen? Draw the timing diagram for a transition from 0 0 when the inputs were go from 0 0 0 to 0 0 1 or something like that. Okay. Timing diagram means this diagram, whatever is shown on the screen. So the input waveform will be, you have to write down the input waveforms and the output waveform depending on how the input is changing. Okay. Uh, any more questions? We still have 1 hour time. Uh, okay. So you have watched the lecture, right? Regarding related to this topic. Have you only read the notes or uh, you should watch the lectures? That is why you're having all these doubts. Okay, it's fine. Even in the PDF, the same slides will be used as a lecture, right? They are just given the slides on it. Okay. Then you should remember something like this. Uh, there is a 1 1 1 1 here, 1 1 1 1 here. Do you remember? There's one example, or you can see the PDF right now. Ah, and they had grouped these two, and these two, and they had said that there's a hazard here because from when there's a one bit change. Wait, was it like this? How was it? Let me see. 4, 48. Yeah. So you had ones like this and ones like this, and the grouping was done in this way to minimize. Right. So here in your groups, you have two terms. Consider these cells, this and this one. There's only a one bit change here, right? Only one bit is changing between these min terms. One of the variables is changing. What I mean to say is this is a bar, b bar, a bar, b, a b, a b bar, c bar, d bar, c bar, d, c d, c d bar. So this block, whatever it is a b c bar d. This block is a bar b c bar d. So only a is changing to a bar. Okay. So in such a case, this static hazard can occur. Okay. Now, why does it static hazard occur? You previously I told you, right? The literal and its complement can take the same value. So this thing has an a. Huh? Oh, who is it? Switched on the mic. So okay, I muted the person. Animesh, are you following me? Okay, there's only a one uh, variable change. So a is changing to a bar. That's all. So b c bar d, whatever it is, it will remain the same, right? And previously I had showed you an example where when a is actually changing to a bar for some amount of time, a and a bar might have both might both have the same value, right? So that might cause you a problem, right? So what you want to do is you have to add one term that is high whenever these two terms are high, right? But it does not contain this a bar or a. So what you could do is you could group this thing. You when you use that, add that extra redundant group. For minimum expression, you don't need that group. But let's say you add that group, it will eliminate the a term. You will get c bar d, and now the function still remains the same, right? There's no change in the function outputs that you're supposed to get. because you're grouping ones. You can add. So if a function has a main term a bar, b bar, c bar, d bar, you can write it as many times as you want in the function. Doesn't change anything because a plus a, and this is actually or. So a or a is simply a. So wherever you have ones, you can add those groups as many times as you want. So when you form this extra group, you get this term, which doesn't change the value of the function. So as far as the function is concerned, having only two groups or having three groups doesn't matter. Now, but the difference is this term doesn't contain any a, right? And whenever this block goes high, this thing will go high, right? Did you understand? And whenever this block is high, this thing will go high, right? Suppose you are transitioning from this one to this one, the c bar d stays high either way. So if you add it to the function output that you get, you AND it with whatever you minimum expression you got, then what will happen? Yeah, it won't depend on what. Yeah, it won't depend on the a. When it comes here, when your input is lies in these two blocks, but suppose your input turned this cell high, then there's no problem. Or suppose it turned this cell high, then there's no problem. There won't be a hazard anyway. Did you understand? No. Yeah, and this thing doesn't work when there are more levels of gates that you need to connect. So if you simply have a canonical SOP, then it's fine. But if you have three layers of circuit, say, and then it might not actually eliminate that hazard. Okay. Any more questions? No questions? Okay, then I'll move on to problem solving. There's a circuit. You can see it clearly, right? No problems, I hope. And you have to get the function. You have to get what x is. So what function does this circuit actually implement? Since there is only 50 minutes left, I will only solve questions like this. I won't give you time to solve. If there are simple questions, then you can try to give the answer. Okay. So this is, you have a and b given to an AND gate, so you will get a b bar, and e and a b bar are given to AND gate, so it is e dot a b bar, right? And this, the second AND gate, let's call it 1, the second AND gate, that will give you ef. This NOR gate will give you c or d whole bar, which is nothing but c bar d bar, right? And you are ANDing it with f, so this is actually f dot c bar d bar. And the three terms that you have, they are being fed to an OR gate. So an OR gate would give you ef plus e a b bar plus f c bar d bar. An OR gate will give complement of this. Is there an option like that? Okay, there doesn't seem to be an option like that, so we can try to simplify it even more. That whole complement that you have, you can use De Morgan's law and you write it as EF bar dot E AB bar of F C bar D bar. This is E bar plus F bar dot E bar plus AB dot F bar plus C plus D. So F bar plus C plus D you have in this option and option B and option C. The remaining things are looking different. So let's but option C has AB whole bar plus E. But what you have is AB plus E bar. So let's see, let's multiply this out and see if we get the right thing. E bar dot E bar is E bar. E bar dot plus E bar AB and okay. So from these three things you can take E bar common. E bar into 1 plus AB plus F bar plus F bar AB, and you have this term here, and here you have this term. So this thing is nothing but E bar plus F bar AB into F bar plus C plus D. So it's option B. Okay. Next one, A will become A bar when it goes through a NOT gate. B will become B bar, and you add those, you'll get A bar dot B bar. Here it's A and B. Then a NAND gate, so it's AB dot A bar B bar complement, which is option B. Okay. Question number 3. Again we have to find the Boolean expression. How will you do this? NOR gate output will be P plus Q bar. This is Q plus R complement. This is P plus R complement. Q plus R complement. This is this whole thing plus Q plus R complement, whole complement. Here you'll get P plus R complement plus Q plus R complement, whole complement. This is nothing but P plus Q into Q plus R, and this is nothing but P plus R into Q plus R, and these two things are NOR fed to a NOR gate, so you'll get P plus Q into Q plus R plus P plus R into Q plus R, whole complement. Okay, let's call this Y. So Y, you can take out the Q plus R common. You will get There are multiple ways you can do this. I'm seeing which one is better. Okay, I'll take q plus r common. What will I get? P plus q plus p plus r. This is nothing but p plus q plus r complement. And then there was this distributive property of addition with multiplication. That is a plus bc is a plus b into a plus c. So this thing you can write this as 0 plus q plus r, and this thing you can write it as your b here. So you can write it as your a, and this is b and this is c. So what is you have a plus b into a plus c. So the answer is a plus bc. Q plus r is a plus bc is p dot 0 whole complement. It is q plus r complement. So it's option A. Did everyone understand that? You just need to simplify, that's all. Any doubts in any of these steps? You could do it differently also. You might have expanded these terms p plus q into q plus r. You could have written that as pq plus q plus qr. Maybe that would have been easier, I don't know. Okay. Identify the logic gate carried out by the following circuit. Who will tell me the answer? And fine. What about this one? Somebody said and. Let's see. We'll check it. It's and or R. Say bar. B bar. A bar dot B bar. Whole bar. Just A or B. So it's R. Okay. Someone said and. Did you understand this point? Or you have any confusion? No problem here, right? Okay then. Okay. A is 1 and B is 1. What will be the values of Y and Z? So this is 1. This is 1. 1 inverted is 0. 0 times whatever you get, that is again 0. Right? And 1 or 1, that is 1. This is 1, this is 0. 0 or 1 is 1. So Y is 0, Z is 1. Right? Okay. C is equal to 0. Then what is the expression for Y? C is 0. So this thing is 0. This thing is 1. So you have a 1 here. When you have a 1 here, what does that mean? Let's say this thing is X. Y is X bar. So whatever you get here, X, you just need to complement that. And what do you get there? This link will give you AB. This is A nor B, which is A or B complement. Nothing but A bar B bar by De Morgan's law. Odd with 0. Odd with 0, you'll get the same thing back. A bar B bar. AB and A bar B bar are odd. So X is A B or A bar B bar. So Y is the complement. What is this thing? XNOR. I mean this thing. X is XNOR. This is XNOR gate. Y is XOR gate. If you meant Y is XOR gate, then you are correct. It's this one. A B bar plus A bar B. Okay. What about question 8? But exclusive OR is not given as. Yeah. If they had given exclusive OR option, then that would have also been right. Because both XOR and XNOR are suitable for comparing bits. But yeah, it depends on what output you want. But both of them will compare bits. Okay. So, but I remember there was some circuit called a comparator, where if two numbers were equal, then you would get an output high. So in that sense, maybe XNOR gate would have been preferred instead of XOR gate. Because for XOR, if both the inputs are the same, then you'll get a low. It still compares the inputs, but it depends on what output you prefer when both are same. Okay, two input exclusive NOR. Minimum number of NAND gates required to implement a function. You can take common, you get A into 1 plus B bar plus B bar C. 1 plus any literal is just 1, anything else is 1. So this is A and 1. This is nothing but A. So if someone gives you an input A, if you want to get the output as A, what do you do? Nothing, you just, yeah, you can simply give it out back to them. Okay. The CMOS inverter, the output voltage is measured across. What is the answer? Does somebody else think there's a different answer? Or is there everyone else source? Okay, anybody else? Any other answers? You can go back to the circuit. Of course, in the exam, you won't have the circuit with you, so you should remember it. This is the inverter, right? So, yeah, this thing is the drain of the NMOS. No, that is the source of the NMOS. Right? This is the drain, if I remember correctly. And for PMOS, this is the drain, and this is the source. But the voltage you are measuring is between these 2 points, between your ground level and this point, which is connected to source of NMOS. Or did I get myself confused? Okay, it seems I have confused myself. 10th one. Yeah, A is the right answer. Then where did okay, then okay, so this is drain and this is source. Okay, okay. Why is it called drain and source? Yeah. So if you simply had an NMOS circuit, VDD, NMOS, then gate. So this is at 0 volts, this is at 5 volts. Uh, in an NMOS, when you apply a positive input to the gate, let's say you apply 5 volts, then this 5 volts will attract electrons from this ground towards it. But there's a dielectric here, so these electrons can't actually go here, they can't pass through. But they, due to the attraction, they'll come to this place. And then since they can't go here, they'll see where else they go. Electrons want to go towards higher potential. So since this point is also at 5 volts, they'll say, okay, I can't go here, I'll simply go here. So this ground is supplying you with electrons. That's why it's the source. And these electrons will go and go outside from here. So it's like a drain for the electrons. But in the PMOS circuit, the majority carriers, they are holes. Holes, you can think of them as some kind of positively charged particle. Actually, there is no particle there. There's just empty space, but they kind of behave as if there are some positively charged particles there. So what will happen is when you give a low voltage here to the gate, that will what will it do? That will cause the electrons to go from this high voltage to this low voltage. It will attract them here, attract the electrons. But the electrons can't pass through because there's a dielectric there. So they will see that there's a ground here, low voltage here. They'll say, okay, we are come here already. This thing has pulled us. So we'll go this way. The hole movement is exactly opposite to the electron movement. So the holes are actually going the opposite direction. So this is kind of like a source to your holes. So this is a source and the holes will exit from here. So this is like your drain. So in the PMOS, the drain is connected to high voltage and source is connected to low voltage. And in NMOS, the source is connected to low voltage. Um, is that right? Or did I make a mistake? Anyway, this is drain for NMOS. This is a source for NMOS. You are measuring voltage between drain of the NMOS and ground. That part is at least clear, right? Wait. I'll explain that again. This time I'll get it right. This is VDD. This is the gate. I'm considering NMOS, so there's no bubble here. That means the input is taken as is. If its input is high, this will think of it as, you can think of it as high, it's active high input. And this is gate voltage, this is ground. So when you give a high voltage that is equal to VDD here, electrons are attracted from the ground to go towards the gate, and since they can't pass through the dielectric present in between, here there will be a dielectric, they simply pass on towards the source. So this is the this is the source which is sourcing the electrons for the NMOS. This is the drain. That is for NMOS. Any questions here? Is that understood by everyone? Someone should reply. Okay. And let's check for PMOS. Okay, for PMOS, suppose you give a 0 volts. Now for PMOS, you take the holes. The direction of the holes is important, and holes can be thought of as positively charged particles. So this is at low voltage, this is at high voltage, so at plus 5 volts. So the positively charged kind of holes will try to go towards the gate, because positively charged particles move from high voltage to low voltage. And since they can't go through the gate here because of the dielectric, they will come here towards the ground. Right, so this is the source, and the holes are getting drained here. Or alternatively, you can think of the electrons which will get kind of attracted from the ground to this place and then go. It's easier to think of in terms of holes for PMOS. Any doubts here? No doubts. Ah, here you give plus 5 volts to the gate, and here you give 0 volts. Is that what you're asking? That's how this transistor is made. Okay. So what you want your transistor to do is, you want your transistor to act like a switch. So it's, you have a switch here, and your gate voltage will tell you whether the switch is closed or it's open. So suppose you had a bulb here. When the switch is closed, the bulb will glow. When the switch is open, the bulb won't glow. Right? And for this NMOS transistor, when gate voltage is high, then the switch is closed. So a circuit is formed. Okay. But for PMOS, it's the opposite. If you give a low voltage to this gate, then it will close. If you give a high voltage, it will stay open. That is by the design of the transistors. Okay. Okay. So I hope nobody got confused, because I myself got confused. Okay. So we had from drain of NMOS transistor and ground. So these 10 questions were from previous year NPTEL assignments. So they'll be helpful to you towards the NPTEL exam and week 4 assignments. The next whatever questions I will discuss, I have taken from previous year papers, gate papers. So I saw that a few students were interested in gate questions. Okay, 001. Let's see. For such type of questions, it's simply easier to try out all the options instead of, or you could also write the simplified expression for x. You could write the expression for x and substitute there, or you could just simply write it out here. The thing is, you shouldn't forget which inputs gave you which output. So 101. This thing this is a XOR b. This thing is b x nor c. So b XOR c whole bar, and this thing is simply c. So for x to be 1, what is the condition? Firstly, all inputs to the AND gate should be 1, right? By definition of AND gate. That's what an AND gate means. So C should be 1. That is true for all the options. And then, why Animesh? You want to leave? Uh, I'll do for 10 more minutes and then I'll stop. I'll continue the remaining questions. Remaining questions I'll continue later, next week. Okay. Uh, so all three must be high. All three inputs to the AND gate. So C must be high. That is true for all options. A XOR B must be high. That is A and B must be different. It should be 0 1 or 1 0. So option B is wrong because it has 0 0. Option C is also wrong because it has 1 1. Then B XOR C must also be high. That is B and C should have the same value. They must be 0 0 and 1 1. So this thing also doesn't work. But this thing is fine. So 0 XOR 1 is 1. 1 XOR 1 is also 1. And C is 1. So we'll get an output high. So this is the right option. Okay. They've asked a simplified boolean for the expression, a simplified boolean expression for the output. Um, this is AB bar, and this bubble here represents a NOT operation. So the input here, you can think of it, the input to the NAND gate as B bar. So it's AB bar into B bar whole bar, and then this is, what is it, A bar plus uh, this is AB plus B, right? If you use De Morgan's law, which is nothing but B into 1 plus A. So, which is nothing but B. So this thing is equal to B. So you have B and B bar here. So B into B bar is 0. But this is an AND gate. So it's B bar whole bar. So it is 1. And 1 plus anything that comes here is 1. And since it's an OR gate, you will get a 0 as the output. So it should have been 0, but none of the options say 0. So I think there's some problem with the question. Okay, if somebody can somehow get one of the options as the right expression, then tell me next week, because I was not able to get any of the options. Okay, I think since this question is from 2000 ECE paper, so maybe they made a mistake. I don't know. Okay, next. Which one? That doesn't matter. See, for this, let's call it gate number one. For this gate number one input is B. The other input is B bar. B into B bar, B and B bar when you NAND, you will get 1 always. And 1 added to anything you get from here, from 2, it doesn't matter. This will always give you a 0. It's an OR gate. So I think the problem was this should have been B bar. Then what would happen? B bar into B bar whole bar is just B. So you get a B here. And this thing would have been B bar plus C whole bar, which is BC bar. So this thing would have been B plus BC bar whole bar. This is nothing but B into 1 plus C bar, which is B bar. And even in that case, you got a B bar there. So somewhere they should have given a different expression. Okay, you try it out and tell me next week if someone gets the proper answer. Next question, 2's complement representation of minus 17. Is it D? 2's complement. So 8421 16 17 1001. That's plus 17, right? That's 2's complement. So 1's complement is 0 triple 1 0. 2's complement you have to. It's a B. You have to add one. It's 2's complement. See, 17 is 1 triple 0 1. 1's complement is 0 triple 1 0. And to get 2's complement, you have to add a 1, right? So it's 0 followed by 4 ones. So it's option B. So given no in 2's complement form. Huh. See, this question you asked in a previous lecture also, right? Some similar question was there. I think Animesh or somebody had asked. Wait, let me see. Yeah. Okay. Okay, okay. I get your point. So for 2's complement representation, what is it? You can only go from minus 2 to the n minus 1 to plus 2 to the n minus 1 minus 1, right? So with n is equal to 5 bits, how much can you count? N is equal to 4 bits. You right. With 5 bits, you can count from minus 2 power 4 minus 16 to plus 15. So with 5 bits, you can't actually count minus 17 at all. You can only go from minus 16 to plus 15, right? So 2's complement representation of minus 17, you'll have to take one more bit, 6 bits, right? Then you'll get 1 0 triple 1. So this will be minus 17. I guess since none of the options matches with the correct answer, then you will only have to think what the examiner might have thought, which is this. They just took 17 and did 2's complement. So it's actually not 2's complement representation of minus 17. It's just 2's complement operation done on the number minus 17. Okay. 2's complement of when you do 2's complement of 17, if there is no overflow, right? If you are within the range of the numbers that you don't count, you will get minus 17. Whatever you get is minus 17. See, what is 2's complement? You just subtract from 2 power n. If you have a number x, you subtract from 2 power n. And in binary, what does that mean? So x is say some 4-bit word. N is equal to 4. Then 2 power n uh, is 16, which is 10000. So 11000, if you subtract this, that just means you're doing 2's complement. Okay, that's the operation which is called 2's complement of a number. Now, what? See, the 2's complement of a positive number is just the 2 complement representation of a number is just the number itself if it's positive. Yeah, when you but you still call it the 2's complement representation, right? For the positive numbers also. No, you can't do 2's complement. You shouldn't do 2's complement. If you do 2's complement, you'll get the negative of the positive number. That representation. Yeah. Huh? What should be? It should be. That's the only thing that makes sense. Yeah. So actually, you should have taken 6 bits if you wanted to represent minus 17 properly. But here, whoever said the question, maybe they did it intentionally. Maybe they just made a mistake. Yeah. Maybe the question is wrong. It was similar to this one also, right? This one was also there was a mistake. None of the options actually worked out. So this is a 2000 paper. So that time maybe they didn't check it too much. I don't know. Or if okay. Uh, uh, See, then what does sign magnitude representation even mean then? It's a way of representing numbers, right? Ah, in the sign magnitude representation, you have one bit spared for the sign. Similarly, in two's complement representation, the positive numbers are written as is and negative numbers you subtract from. Ah, then this statement does not make sense, right? The two complement representation, you can only represent numbers from minus 2 power n minus 1 to plus 2 power n minus 1 minus 1. That statement was given in class, right? Then that would make no sense because they are actually counting to from 0 to plus 2 power n minus 1 minus 1. How is that possible? That is, yeah. No, wait, let me deal with the other question first. Ah, go ahead. Who was it? Yeah, yeah. Then you can represent minus 17. I've already done it right. 101111. That is minus 17. Yeah, okay. That is fine. But the other question, the other person, who was it? No, was one of you had an issue with what you mean by two's complement representation, right? Where did you see that whatever you said? It's okay. If you don't feel that it is correct, you can tell. No need to say silent. Was it Neetu? Whatever. Why are you staying silent? It's okay. See, then this statement was given in class, right? 2's complement is used to represent only negative numbers. Then what is this range that was given? Minus 2 power n minus 1 to plus 2 power n minus 1 minus 1. For even for n for 1's complement, they had given it as minus 2 power n minus 1 minus 1 to plus 2 power n minus 1 minus 1. They said using 1's complement representation, you can represent whatever I have given. Then the statements said that two's complement using two's complement representation, you can represent numbers from minus 16 to plus 15, right? What does that mean? If you can represent only negative numbers, then how did they count till plus 15? How did you get D? Hmm. 101111. One. Yeah, yes, yes. That's minus 17. Okay, but that Huh. When you do 2's complement, you will get black plus 17, right? No, no, no. How is that right? 1001 means something else in 2's complement representation. 2's complementation representation of plus 17 is 10001. Option D of plus 17. Right. It would be 010001. You took 6 bits. See, no, see, you understood that thing wrong. You can represent positive numbers. You don't do the operation when you don't subtract from anything. You don't do anything to positive numbers. You keep them as is. For positive numbers, that itself is called the two's complement representation. Two's complement doing the two's complement operation is different, or the function called two's complement is different from the two's complement representation of a number. See, if you understand it that way, none of this thing makes sense. No, none of what was taught in the lecture will make sense. So maybe it's defined that way in some other textbook or some other place, but you can't think of it there in that way here, at least for this course, and you will end up in trouble if you do that. Which lecture was that? Two's complement and one's complement. Lecture 6 or 7, right? It is in week 2. If anybody wants to leave, you can leave. Animesh, you can leave. I'll just discuss this thing and end the session. Okay? I will cover remaining questions next week. Uh, whoever stays can continue discussing this question. See, I'm trying to open that PDF from week 2. See, here they have given two's complement. If you have a number x and you want to do two's complement, then you do 2 power n minus x. Right? This doesn't take two's complement representation of this number. Simply says this is what you mean by doing the two's complement of a number. Okay? Similarly, one's complement. It's just an operation that you do on any number that is given to you. If you have some number x, you can do one's complement. That is just flipping the bits. Or in actuality, you are subtracting the number from 2 power n minus 1. In our case, x is negative, yes. Uh, Yes, but that's not exactly how it works. Where did it go? It's not in week two also. I get it's in week one. No, that's not it. Okay, I don't have week one. Give me just 1 minute. I'll go to the. Ah, who is asking? See, you can you asked the question and now you want to leave. Yeah. Wait, I'll just give me 1 minute. Yeah, then you can leave. See, what is this? Ah, see, signed ones, twos, and these are the representations. Okay, so zero also has a representation in ones and twos, complement representation. They have given the representation for positive numbers also. So in the number representation, positive numbers are just the same in all three ways of representing a number. But when you are representing negative numbers, the way you do it is different in different systems. In sign system, you use the extra bit. You use bit B3 as a sign bit, so you flip it to one. So if you have 0001, you just flip B3 and you get 1001. Actually, in the normal number representation, 1001 should have been 9, right? In sign representation, the same pattern 1001 that you use for 9 is actually used for minus 1 instead of 9. The same thing happens here also. You have 16 patterns, so you can represent 16 numbers in all three forms. Only thing is, in these forms, you use half of those patterns for one type of number, positive numbers, and half of those patterns for negative numbers. Okay, that's it. If you're still not convinced, maybe you can go and find some textbooks and see. Okay, that's it for today's lecture. Uh, we solved only 13 questions, but I'll try to solve more questions next lecture. Okay, thank you for attending. Anyone- if anyone still has a doubt, I'll stay. Is it? Okay, we'll see it next class then. Uh, I'll also check once again. Usually, you won't have an overflow. Here, you are not supposed to represent minus 17 with only 5 bits. You're supposed to use 6 bits for that, but the options all are with 5 bits. That's the problem. See, with 5 bits, you should not even be able to represent minus 17. For positive numbers, yes, you can ignore the positive terms there. That is true only because they work uh, a normal number system where there are weights to each of the bits, right? So it's like if you take a decimal number, you have a hundreds place, tens place, and units place, and you multiply that out. Units place you multiply by one, tens place you multiply by 10, and hundreds by 100. So if you have a 0 in hundreds place, you can simply say that is 0 times 100, which is 0. So it's not actually contributing. So I'll write out only the tens and units place. That is okay for normal number system. But in signed and there's two's complement and one's complement representation, that doesn't hold anymore. You can't simply multiply out the digits 0 or 1 that you have with the weights. You will get some different numbers. What happens in these two representations is that instead of counting from 0 all the way to 2 power n minus 1, we are only counting from 0 up to 2 to the power n minus 1 uh, in the positive direction. And for the negative numbers, with the remaining patterns that we have, we are giving that to negative numbers. So at the end of the day, when you see a pattern, it is up to you how you interpret it, right? As there's no rule saying this must be 2. I could have called this 2 also. This would be a number. Uh, uh. See, but if you do the 2's complement for this number, you'll actually get plus 17, not minus 17. No, no, that's not. No, that's not what they're asking though. Uh, the I think the question they framed it in a peculiar way. That's the problem here. What they mean is in a two's complement representation system, if you had a system to represent numbers. See, if you have n bits, you have 2 power n patterns, right? Of arranging those bits as 0, you can give 0 or 1 to each of the bits. There are two ways of doing that for each bit. If you have n bits, then there are two ways for each bit, so you have 2 power n different patterns. These patterns, it does not always have to represent numbers itself. For example, when you open Photoshop, some pattern, say just my number itself 1001, it might simply represent the colors red or some color blue, something like that. But if you open a text document, the same binary number stored in your computer, it might represent a letter. Say, let's say it represents a letter A. So what this pattern of bits means is up to you, up to human interpretation. So what we have done, it turns out that when you use number systems in the normal way without any signed numbers, it just turns out that we can use that place value method to find out the value of the number in decimal. But when you are using two's complement representation and one's complement representation, it's that is thrown out the window. You can't multiply by place value and write it out. So here you are arbitrarily assigning some patterns that were supposed to represent positive numbers. You're taking those patterns and you're saying, okay, I don't need these positive numbers. Instead of positive numbers, I'll say this number is a negative number. For example, instead of this 101111 in a normal number system, this would have been what? This is 1 plus 2 is 3 plus 4 is 7 plus 8 is 15 plus 32. So this number should have been 47 if you treated some. But we are saying, okay, maybe my system doesn't care about the number 47. Maybe I won't use it anyway in my system. There could be some circuit. So instead of wasting this representation, this is a pattern that I could have used, right, to represent something. Maybe I could use, say, if this is the outputs of your if this is the bits that you have, maybe I could say, give me color red. That would also be done. Or maybe you could say, if this is the bit pattern that you get as the output, then you have to play a musical note of some frequency, say 220 hertz. So you're saying, instead of wasting this bit pattern only on the number plus 47, I could represent a negative number instead. Yeah, you are restricting yourself to certain range, and which negative number you will assign this to. That you could do it in multiple ways, right? But in this two's complement representation, there's only one unique way in which you can. It's kind of a mapping that tells you which useless pattern you can give to a which negative number. So they say the pattern for 47 that we usually use, we'll say it's not 47, it is minus 17. So it's kind of a function, a mapping. Yeah. Usually, this type of question, wherever I have seen, uh, if whatever method whatever you think of is wrong, then you just think of the other method. That's all. So for this should have been 101111, right? But there's no option that says that. So you simply do 2's complement of 17 and write whatever you get. If you do that, you'll get 01111 if you do it with 5 bits. So you just mark that as the right answer. Because there in the exam, there's nothing you can do, right? You can't go and question them. Maybe later they will give grace marks, but in the exam hall you can do. Yeah. So even if you think something else is the right answer, you should just take whatever answer that the exam whoever set the paper thought on. Yeah, there'll be negative marks, right? So maybe you can just leave it. Maybe later they'll give grace marks saying that this was not proper. Okay. If there are no other questions, I'll end this session. Yeah, next time I will try to discuss more problems that are not really, see, these kinds of problems, they are not there in our assignment, so it will be nice. Okay, thank you.